Yeah.
Good. So I would like to thank him, because now I know I have to speak for 1 hour, so I have a lot of time, so feel free to interrupt me. And please interrupt me, I have some time to fill. Okay, so let's go. So first, I will speak a little bit about quantum mechanics very fast, very quickly. First, a qubit, so your quantum unit of information. Sorry? Critical? Okay, you see a nutshell? More tiny. More tiny. You can Wikipedia this, and you'll see. It's very interesting.
Dr. Isn't that the little bear-like animal?
Yes, and the cuticle is the shell of the tardigrade. Okay, so you have the quantum. Thank you for the interruption. So you have the qubit, which is a quantum unit of information. It is a superposition of 0 and 1. The beginning of the talk will be very slow, so okay. And then formally, this is a weighted superposition, and those are complex numbers. So formally, a qubit, just see it as a vector in a complex vector space of dimension 2. And then I just recall some definition when you are in this kind of space. A unitary, here you have a dagger, you take the transpose, and you conjugate all the coefficients of the matrix. This is the definition of a unitary, and this is the definition of an isometry. Okay. And in quantum, you have this phenomenon that if you observe a qubit, if you measure it, then you will see either 0 or 1 with a probability which is the square of the modulus of A and B. So who never heard about all of this? No, I think it's quite clear for everyone. Okay, so here is maybe the most outrageous claim of this talk, that quantum processes, you can model them just by the category of finite dimensional vector spaces, complex vector spaces, and isometries between them. Okay. But this is only for pure quantum mechanics. You are not able using this to really explain what is a measurement or what is a classical process, which is a shame because most of the humans only care about classical processes. And to do this, you need to go further. There is another category, which is a trace-preserving completely positive maps. So, okay, so I will not explain clearly what it is, but you have another category. This is again some vector spaces, and you have an embedding, of course, because this is just more general. Okay? So now what this talk will be about, what I'm doing. In fact, I'm a graphical language designer. So when I design a graphical language, I start from some generators, boxes like that with some numbers of inputs and outputs. And then what I'm doing is I'm composing them using a tensor and composition like this. And then I'm adding some equation and taking the quotient of the three things generating by those generator and those operations. Then this is my graphical language. So I think most of you are doing category theory. So this is in fact presenting a prop by generators and equation, because you see there is only one type of wire. Okay, and then we'll give an interpretation to this. In fact, in each wire, I want a qubit. So the idea that for each diagrams with n inputs and n outputs, I will interpret it, give an interpretation, which is a matrix of size 2 to the m times 2 to the n. Okay? And I want this interpretation to have some properties. First, I want it to be universal. This means I have n-th generators, formally, that I can represent everything I want. So all matrices can be represented. And I also want it to be complete. This means I have enough equation that if our two matrices are equal, I want to be able to show this equality in the world of my diagrams using diagrammatical equivalence. Let me just put it in a categorical language. So I want to present a prop by generators and equations. Okay. My interpretation is the strict monoidal functor. When I say universal, in fact, I mean this interpretation is full. And completeness, it means it is faithful. Okay? And then if I have a universal and complete languages, then it is full and faithful. And usually we have just an equivalence of category if you choose your category well. Okay, so when you have a graphical language, which is nice, and you can stop caring about what is this category, just draw your things. And you know this is the same. So this is what I want to do. I want to represent the isometries and TC-PCM, all the quantum processes. I want just to be able to draw them. And is this possible? So for isometry, you can do circuits. So circuits, we know the generators, but we don't have the equation. So it's not exactly true. Yesterday, Arnie talked about this. In fact, we know it for 2 qubits, And I don't know if you remember the number of equations. No one? 70, yes, 70, which is huge. Usually you have less than 70 equations, and only for 2 qubits. So the idea is this is super hard, it's a really old problem, so let's try to relax our model. We'll consider post-selection quantum mechanics. So the idea is post-selection that you forgot just taking the isometries, you take all linear maps, you say every linear map is okay, and there is a physical interpretation of this. When you have a measurement, you assume that you are able to choose the outcome. So you are very powerful. This is completely unrealistic, but this is the idea. And in fact, when you are relaxing your model in this way, then we know how to design complete and universal graphical language for this. In fact, we have 3 of them. This is the DEX calculus, the W calculus, and the DH calculus. So since I have a lot of time, I give you some time to admire those beautiful languages. So I just put you some rule with some generators, so you can see what it looks like. In fact, all of them are universal and complete.
So,
yes.
As you asked for interruptions,
yeah.
You added some lovely colours to the ZH campus. Is that common?
The colors here?
Yes.
I'm not sure. In fact, I just took the drawing from slides of Renaud Vilmart.
Okay.
So I don't know if those are the usual colors. Okay. Yes, no, I don't know what I'm. Okay, let's see. Yes, of course. Okay, so this is for pure quantum mechanics in the post-selection model. Now, what I want to do is to go there in mixed states, with classical processes. So here we don't know, of course. So if we knew how to make circuits. So this seems to be hard. So why not doing the same thing, going to post-selection and see if we can do something. And this is the point of this talk. We know the category here is called CPM. So you have just complete positive maps. And again, I will not give the definition, sorry. And the point of this talk is to design a graphical language for this. And if possible, just doing this in a nice way by extending those languages. So just adding some generators and equations to do this. So to understand how to do this, let's abstract the thing away. So we'll start by abstracting this. Find an abstract way to present what is a finite dimensional Hilbert space. And this can be done using symmetric, the dagger compact closed symmetric monoidal category. Okay, so let's see the definition. The idea is you have a symmetric monoidal category, okay, and you're adding this, the dagger. So this gives you, for each morphism, you can find a morphism in the other direction between the same object. So there is a physical interpretation to this. You have this property that if you reverse time, you also obtain a physical process which is allowed by the law of physics. Usually highly improbable, but it's allowed. And the idea of this is that if you have this inside your category, then you have a way, if I give you a process, to give me the process you can obtain by reversing time. So it's a very nice way to put a physical idea into the categorical world. So you take this dagger compact category. Identity on objects. This is the idea. Yes, you are identity on object. Yeah, that inside this, since you have this dagger, this formal one, you can formally define isometries and unitaries. Just this way, okay? So this, in fact, is an abstract category when you can define isometries and unitaries. And I saw there are a lot of names for this kind of thing, and this is my proposition. Why do we call them cup-cap categories? Because they are cups and caps. We directly stick to what we mean. And it sounds a little bit like cupcakes, which I like. So this is my proposition. So do whatever you want with it. Okay, so this is the abstraction of finite dimensional Hilbert spaces. So see, I put just here my category with those properties, and then I can define the subcategories of all isometries. Here, just a subcategory, okay? And here, this is my abstraction of what it is, the category of isometries, the pure quantum processes. Okay, so now what I want to do is abstract this part. What do I put there? In fact, it was done, we know. What we do is we build what is called an environment structure for this. Okay. So first, let me just explain a little bit what happened in this world to see. So you want to represent measurements and some probabilistic superposition of things. Okay. And to do this, you go from linear to completely positive maps. And you have new, for example, new operation, you have this. So this is a trace operator, you take the trace of a density matrix. And this means you see you have one input and no outputs. This means you take your qubits, you measure it, and you forget about the results. Okay, so this is the idea of this new thing that you should be able to represent in your new world. And then with this, you can define this abstract property, which is causality. So it means that if you have a process, okay, you apply your process, you just measure and you forget about the results. It's the same thing as just measuring from the start. So this seems to be a completely obvious property for any physical system. And in fact, it holds. So when I say pure, this is just without post-selection. So if there is no post-selection, in fact, things satisfying this are in fact exactly the isometry. That is the really physical processes. Okay, so this is what the kind of things I need to have in my abstraction. And we do this defining the environment structure. So we say that this is an environment structure for C. If first, of course, is a generalization of C. Okay, so if you have new processes, you have a way to embed it, this iota. You need to add this generator, this ground, which is just measuring and forgetting. Okay, and we have some obvious properties about this. And then you can express in an abstract way what it is causality. You just say this. So you have some causal maps inside your environment structure. And of course, when I say pure, in fact, this is because when you are in the image of iota, this means you come from the real world here, okay? Then, so let's stop this from environment structure. So, in fact, this works. This works. It works. We can show that this environment structure are exactly capturing, this is really understanding what it is to be completely positive maps, okay? And we know that if you are an environment structure for Hilbert spaces here, then you are equivalent to this category, okay? Yes?
Can you give an intuitive comment on what is the motivating concept generally behind the environment structure that you're trying to capture in this realism? Intuition.
A little bit later. I can say, okay, the idea that we have, in fact, you have, we know some theorem linking this to this, okay? And the idea to build a structure or just to abstract this theorem. Okay, so I give you more details later if you want. Yes?
You need equations, you need more equations.
Yes, in fact, yes, of course, okay. Yes, this is not everything about environment structure, but I will come back to this later, of course.
It looks like purely syntactic.
Yes, in fact, here I'm just adding some generators. There are no equation at all. Yes, of course you need some equation, and this will be the point later.
And then another thing I would say, like I renamed causality terminality
Okay.
to avoid confusion with all the concepts of causality that are around. And
That's-
for category theory audience, you want to use terminality because that's what it is.
Yes, so this is a complete spoiler of the following of my talk,
Oh, sorry.
and of the remaining of my talk. But it's very good, in fact. Yes. Okay.
I was just going to say, can you
Yeah.
repeat the question because you cannot hear it on the stream, but I guess.
Oh, sorry. So the question that, so Bob said he renamed this causality properties terminology. Because for category theorists it was better. In fact, there is something to do with terminal objects here.
Is that true for all F in C or in C bar?
This definition is in C bar. Okay, you say a process is causal here. But in fact, you can, yes, because this is not in fact in C. So it will not make sense.
That's a
No, I was just
definition of
wondering-
causality rather than a requirement on your system.
So sorry, can you repeat?
Sorry, so a map is called causal if it satisfies that property rather than that is a property that we require all maps to satisfy.
Yes.
I think that's it.
Just, is there a reason why your category is self-job?
Well, it is several, because I mean finite dimension. So for finite dimensional Hilbert space, this is the case. And in fact, this is better because then you can just use one type in your wires for your graphical languages. Else you need to have different types and you need to add some arrows. You need to give orientation to your wires, which is possible but less easy. Okay, so we have this abstraction of environment structure. So the idea that we have the square. So you start from category. Here you have the environment structure. Here you have the isometries. And here you just take the causal maps, and then you can have an abstraction of this part. Okay, so this is a categorical, purely categorical formulation of the previous square I showed you. So let's see if we can use this to design our graphical language. So as I said previously, in fact, you have other properties in the environment structure. First, for all maps, there exists a pure map P, that is it, which is in fact just in C and not in C, or not only in C bar, such that F is of this form. Okay? Is it clear? No. C, it's not clear. Okay. So in C bar, okay, you have C in there plus something else. Okay? And if you have a map F, which is in C bar, in fact, you can always find a P which is in C, such that F can be written in this way. Okay?
Does that mean L?
Sorry?
Does that mean L?
And you map L? Oh, mistake. Sorry. So L and F are the same thing. I'm sorry. You need yeah.
But the composition on the right happens in C bar because the
Yes, of course. This is in C bar and this is in C bar. Okay? But this, in fact, is in. Yeah, when I say it is in C, it is the image of the functor from C to C bar. So everything is clear now? Clearer? Oh yes, I see some people nodding. So it's not. It's better than before. Good. And this is very interesting for a graphical language point of view. So P is called the purification of F. Because it means that just adding this, it's enough for universality. You just need what was previously there, plus this, and you can represent anything. So very good. For universality, we know what we have to do, just add a ground generators. Now the problem is for completeness. So in fact, in an environment structure, you have some equation. You define and you have a kind of okay, so this is the equation. You define this relation, okay, between F and G. Why not? And you ensure this. So this is how you define, this is a complete definition, now you have it, of an environment structure. You ensure this. So this, in fact, is saying something about the uniqueness of purification. You say, okay, if you have a purification, then you are in this same equivalence class. Okay? So if I want my graphical language to be complete, I need to add all, at least in art equation, to be able to show this for all diagrams. And looking at this, I don't know how to do this. So you need this for all those maps. So maybe you need one equation for all possible diagrams, so it's not tractable. So this is a dead end for graphical languages. But there are some light, there are something. You have this result. So if you have a symmetric monoidal category, you say it is affine if the tensor unit is the terminal object. Okay? It's clear for everyone? And then if you have any symmetric monoidal category, you can do the affine completion of it. You just freely make the tensor unit a terminal object. Okay? And in fact, it was shown by Euro and Staton. So I think they are there. But no, okay, yeah. So thank you. This is helpful because then we see here that in fact, then TP-CPM is the affine completion of isometry. So this gives us a new abstract property to use.
Does the affine completion proceed by quotienting maps or by adding a new object?
Okay, no. You already have the object you want. You have the tensor units, and what you do, okay, you have different way to see this, but I think add just a new morphism, okay, for each other object which go towards your tensor units. And then you have the equation saying that, in fact, when you compose with this object, then you're always equal to this one. Okay. And the main property you really need here is to say that the map. Okay, and this is good because now what I can do, so I have this abstraction here, but I will start from C-iso and take the affine completion. Okay. And now, my problem is that I have this thing, and I want to complete it into a square. So I'm asking the question to you, fellow categorician. What will we do? This is a real question, and I will not continue this talk until I have the answer. So just Okay, so what do? We want something here. What do I do?
Put a little exclamation mark over the C.
You say? An exclamation mark over the C?
Exclamation mark over the C.
Okay, so if you do this, then you have, in fact, something here. Okay? But then I want to see also an arrow. This, and you want to complete it into the square. So maybe this is less lateral than I thought. Thing there. We call it this. And this is nice from a graphical language point of view, because when you are doing the push out, in fact, you're just taking those two things, okay? You put them side by side, so you have all the generators and equation, and then you're just adding some equation here. But let's think about this equation, in fact. So here, for C, I already have the equation. I know to represent it perfectly, okay? So now, here, in fact, I have the equation. I'm just adding a new generator, okay, which is this ground, and I'm adding the equation, ensuring that all the isometries are erased, okay? That this is terminal. And then I just have to combine those two here. So it will be clearer later, but in fact, you can understand just seeing this push out that for the equational point of view, this is working. I know how to represent this. So this is our recipe. You choose your favorite graphical language for pure QM, post-selection QM. Then you just add a new generator, the ground, okay? You keep the same equation, you just, okay. And then you ensure that this will erase all isometries. So this is an infinite number of equations, but if you know a spanning set of the isometries, then you just have to ensure this for the elements of your spanning set. And if you have a little spanning set, then there are not a lot of equations. And this is it. So this is the recipe to axiomatize C ground. Okay? But now the big question is C ground an invariant structure? Is C ground really what we want? So I just I show you what are the rules. In fact, if you want to extend ZX, ZW, and ZH, you just need to add this, in fact. And this is done. So not a lot of equation, in fact. And even among those equations, you can remove some. For example, in ZX, you can remove this one. You can prove it from the other. I don't know for ZW or ZH. Yeah?
So what is the semantic interpretation
of this? Okay, the idea is that each time you need a spanning set of isometries, but the different languages will not be able to represent nicely the same isometries. So in for each here, we use a different spanning set of isometries. So I can tell you for ZX, because this is a language I know. For the other, I'm not really sure, but I think you can guess. So here, just a phase, which is an isometry. Okay, so you can set it. Here, just a ket, which is an isometry. Ket 0,
so
you can set it.
Is there a natural interpretation of that syntactic ground element itself?
Here? Oh, the syntax?
Yes.
Oh, you go into completely positive maps, and you take the trace.
Okay.
This is a trace. Yeah, sorry.
Question.
Yes?
Go back one slide, please.
Yes, of course. Oh, okay. Yes. No problem. Whoa, I still have a lot of time. Good. So now it remains to show that this is in fact the invariant structure. Okay? So is it? So in fact, what we have done, so I will define a new equivalence relation like this. So you say that F is iso with G. If you have some isometries, you can put there, okay? And they are equal, okay? And in fact, in our construction, our C ground, this is how you show that something is equal, okay? If you are, this is a transitive closure of this relation. So this means you have a lot of isometries you can put there, okay? And in fact, you have this. Why? Because you see, you have F and J, and you can put a lot of isometries there, okay? Here. And then the ground will erase all of them. So you see, if you have this, you can show this, and in fact, it's an equivalence. So our equality is described as this relation in the plus. And if you remember, the equality in invariant structure, it was with another equivalence relation, it was CP, okay? And in fact, we know that this is always included in this one. So we just have defined a weaker notion of equality, okay? But if we are able, in our category, to show that two things are equal, it will be equal in the environment structure. So the big question is to know that if the converse holds, are those two equivalence relations equal? And this will be very nice because it means that we have a universal and complete description of environment structure and so of mixed-state quantum mechanics. And you have a theorem, which is the Stein-Spring dilation theorem in operator theory, which says yes. So this is my version of Stein-Spring dilation theorem. It says you have this, in fact. So in F-Hilb, it's good. We have it. And for the subcategory of qubits in F-Hilb, so this is what I care about. I just want my wires to be qubits. Yeah. It still hold. It's OK. You can show this. And this is very good. So this means I'm done. I have what I want. And then even more, if you just take stabilizer quantum mechanics, which is a fragment, something I don't know, smaller, yeah, and it works again. So it's very good. In fact, this seems to be true that our construction is just a simpler way to say what is an environment structure, but it's not. We have also counterexample for Clifford plus T quantum mechanics, which is another fragment. Then this is it fails. You're not able to use our equation to show all the equalities you would like to have. So for this is still an open problem to express what it is to do mixed-state quantum mechanics in this fragment. OK. So in fact, it's almost done. Just a quick, to sum up rapidly, quickly. Yes?
It seems obvious if you start mixing Clifford plus T that whatever you get is not going to be Clifford plus T. Because you've got this discrete approximation structure, and mixing is something you use a continuous variable with.
OK.
Is that the reason it fails?
Why it fails? In fact, OK, so maybe this is we can discuss about it. So the reason it fails, in fact, is because you are representing some matrices. And in fact, we know that for Clifford plus T, we exactly know what is the field, the coefficient of our matrices. And those coefficients, you are not able to represent some numbers. For example, if I remember well, I think you're not able to do a square root of 5. Yeah. And this is a problem that if you are taking, so a counterexample, very simple, is this. You take, so I hope I remember, you take 1 plus I, okay? And in fact, this should be equivalent in mixed states to this, because it's just the complex conjugate. But if you want to find any map to multiply here, if you want anything to, if you want to find a u doing this, then you will need square root of 5 to express the u, because this is a modulus of this. And then you start, it's not possible. But if you have an interpretation thinking about the approximal universality, I would be happy to understand this a little bit more. OK, so to sum up, if you want universality, you start from a language and you have the ground. Then, if there are enough isometries, then you just have to ensure that the causality, so you array them. And if you have a little spanning set, then you have a little number of equations. OK, so it's almost, I still have a lot of time. So let me just show you this. So this is where we are. So for finite dimensional Hilbert space, we have 3 graphical languages. And with our result, we can extend it directly to CPM. So here we have what we want. And we have, in fact, more. If we know something for circuits, we know how to extend it. Just add this and make it a terminal object. Okay? So the only missing pieces of this puzzle is to find the complete set of equations for circuits for all qubits. This seems hard, but we hope in. OK. Good. So I think we have a lot of time. So I think I would like to say something about this. And in fact, well, if you want a question, you can.
Yeah, you're.
Oh yes. So you are not listening anything anymore. Right? Yeah, in fact, you were listening to my shoes for a long time.
Surprisingly.
enough. I think it sounded okay.
Good, 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 good. Okay, in fact, you see here, we start to have a lot of expressive power in ZX calculus. We can do a lot of things now. We have this, we have different construction. And to show you this, I would like to present you a quick quantum algorithm and see how we can use these things for real. Okay. So let's do this. Hop. Are you seeing this here? You are seeing everything? I know here you are not, because I tried and I know it's very difficult for you, but will it be okay? Okay. Yes, but here, for you, it will be a complete nightmare, no? No? Here you see? Okay, let's see it. So I will draw you a quantum algorithm very quickly. So the idea is you have a function f, okay, which goes from